Hi, this is Akshada Hande. I'm working with Dr. Kroll, and in this project, I'm doing a comparative study on inert versus reactive atmosphere pyrolysis of PHC20 derived SiCN ceramics. We are working on polymer derived ceramics, which are produced by processing a liquid polymer precursors at lower temperature, followed by heat treatment at higher temperatures. This process is called pyrolysis, and normally, inert atmospheres are used during this process. In my work, I'm using hydrogen, which is a reactive atmosphere, and I would like to study how it impacts the chemistry of resultant ceramics. I'm using a commercially available liquid polymer precursor, PSC20. It is used in the synthesis of SiCN as it has SiN in its backbone. Many groups are already working with reactive atmospheres, but these studies are done on either SiC or SiCOs. Some of the groups have worked with SiCN, but atmosphere used was mostly ammonia. So I first cross-linked the PSC20 using dicumyl peroxide to get hard solid, and then it was ball milled to get fine powders. These fine powders were pyrolyzed in two steps. In first step, we get the amorphous ceramic, and in second, we get the crystalline ceramics. We already see the differences in amorphous ceramics. Uh, uh, Under nitrogen, we get the black sample. Under hydrogen, it is not black. Black color is the significance of presence of free carbon. Free carbon basically is a carbon which is bonded to other carbon atom only. When it is attached to different atoms such as silicon or hydrogen is called a carbonic carbon. We performed the IR for these amorphous materials N10 and H10. In H10, we see the peak for SiC vibration, which suggests the presence of carbonic carbon. Then the XRD analysis was done for the crystalline sample. The ceramic pyrolyzed under nitrogen, which has a red spectra. It matches with the XRD pattern of SiC, whereas for the blue spectra, which was for the ceramic pyrolyzed under hydrogen, has more peaks, which suggests the presence of multiple phases. Then this data was analyzed further for quantitative phase determination using software JADE, and we got the weight percentages of each phases present. In the ceramics pyrolyzed under nitrogen, we got almost 90%, 95% of SiC, whereas for the ceramic pyrolyzed under hydrogen, we have 70% SiC and 30% Si3N4. The data for N10 AR15 matches with the literature value for the PSC20 pyrolyzed at 1500 degrees Celsius under inert atmosphere. And the reason for single phase is the carbothermal reduction of Si3N4, which in which Si3N4 reacts with free carbon to convert itself into SiC. As we have 30% Si3N4 in the sample pyrolyzed under hydrogen, it means there was not enough free carbon present for the carbothermal reduction. We also did the mass loss studies for this pyrolysis. For the samples pyrolyzed under hydrogen, we had more mass loss than the samples pyrolyzed under nitrogen. The mass loss in the first step for H10 was related to the evolution of CH4, which is released by the reaction of free carbon with the hydrogen. As we have more mass loss, that means more free carbon was released in the form of CH4. So to summarize, SiCN produced under hydrogen has less free carbon than compared to the SiCN produced under nitrogen, and is indicated by non-black color of H10, presence of sp3-like carbon in H10, presence of Si3N4 in H10 AR15, and higher mass loss in H10. I would like to thank NSF for their funding. Thank you.